Thank you. Thanks for invitation and thanks for kind introduction. So in my mini course, I will talk about the Margulis and Zimmer's cocycle super-rigidity. At first, I thought that I want to give a proof, but it looks like it's too technical, and it's more good idea to give you some idea why they are very useful and why that arise the so-called Zimmer program, because this trimester is about the Zimmer program and group actions. So I will not give the proof of the super-rigidity result, but instead I will focus on the statement itself and then why this is useful. So today we will focus on the cocycles. And tomorrow, I think that tomorrow is the second lecture. Tomorrow we will state, or we will see the statement of super-rigidity and give some idea. And the statement itself will be quite complicated. So we focus on the statement itself and why this can give some information about the lattice sections, especially about the entropy or Lyapunov exponent. And the last lecture, if time permits, then I want to give you some techniques or some lemmas we used over and over again. But anyway, so let's start with the, I should use the button. So let's start with the cocycle. So in order to avoid many technical difficulties, G and H are groups, but for me, groups are nice groups. So if you want to put any kind of topological assumption, then that's fine. So locally compact, second countable, and what, metrizable or something like that. So G and H are topological group, which is very nice. And even actually, you can only think about the matrix groups. Something like SL3R or something like that. So G and H are nice groups, and S and mu will be the so-called Lubeck space. But if you are not familiar with what is the Lubeck space, that is fine. You can just think about the S is the just set with sigma algebra, and mu is the probability measure on there. So this is just, you can just think Lubeck space as the set with sigma algebra, and mu is the probability measure. And why do I call this is Lubeck space? Because I don't want to consider something like R with the discrete topology and then Borel sigma algebra for the discrete topology. I don't want to care about that kind of some pathological sigma algebra, but something like manifold with Borel sigma algebra or some complete separable metric space with the Borel sigma algebra, they are all quite nice. So, but for me now, just S is a set with sigma algebra, and mu is the Borel probability measure. So now I want to give you the definition. So let's say alpha is the map from G times S to H is the measurable map. Alpha is called, sometimes called measurable cocycle. If for all G1 and G2 in G, and let me see. Let me write down the statement and then say more. Alpha of G1, G2, comma S is same as alpha of G1, comma G2 dot S. And now I need one more assumption where G acting on S mu by, let's say, measure preserving, or mu is G quasi-invariant. That means, so here quasi-invariant means that if mu of A is 0, if and only if mu of GA is 0 for every G. So this is somehow the weaker version of the invariance. So if mu is G invariant, that means that mu A is same as mu GA. But now I only want to care about the mu A equals 0 if and only if the mu GA equals 0. So I want to say that the G action preserves the measure class of mu. But you can now, again, you can just think about the mu is mu is G invariant Borel probability measure. You can just think like that. So now I have an action. So this central dot is, I will always use the dot for the group action. So G2 act on S. So I can have this, but now this is not the end of the equation. So I want to say that G1, G2 dot S, and alpha of G2 S for mu almost every S. So this is called the cocycle equation. And it looks like, at first it looks like quite weird, why do we care about this kind of object? But I will give you, this cocycle appears very naturally in dynamics. So I will give you some examples later. But maybe if you are very curious about some measure theory, then maybe there is something weird happens in here, because this is for every G1 and G2, there is some full measure set so that this equation holds. So maybe you can ask that this full measure set may depend on the G1 and G2. So this is somehow very technical things. But for us, we may assume that this, let's say this is star holds for all G1 and G2 in G and S in S. Actually, this is possible up to changing the null set. So there, more precisely, you can find alpha prime, which is the measurable map, but satisfies this equation every S for and every G1 and G2, so that alpha and alpha prime are same almost everywhere. So that's fine. Yeah, that's also fine. Yeah, so at the end, that's also fine. But I do not have a measure on G. So now, right now, I don't have a measure on G, so that's the thing. But now, actually, this is too high. So from now on, let's just care about the cocycle, which is defined everywhere. And so here is the example. The first example, or zeroth example, is that the representation, or homomorphism. So if you have a homomorphism, because they are group, you can have a group homomorphism. We can define the cocycle by just pi of G, right? So this is the first example of the cocycle, and I want to say that cocycle is somehow the generalization of the homomorphism. So, but this is quite trivial, cocycle. But now the somehow interesting example appears when you have a group action. So let's say M. Now M is smooth manifold. Let's say smooth compact manifold. And now let's say mu is the G invariant Borel probability measure. And then in order to avoid technical difficulty, let's just say that, or basically you can do that. So I can actually trivialize the tangent bundle. So this is the tangent bundle, and this is the dimension of the M. And actually there is a way to trivialize measurably. If you cannot believe me, then maybe you can just think about if you think about basically you can just let me just believe this. So you can think about the frame bundle of M, and then you can choose a measurable section of the frame bundle. That measurable section will give the measurable trivialization. But again, you can just assume that M is parallelizable, so that tangent bundle is actually trivial. But measurably, we can always trivialize the tangent bundle. Then now, what does this mean, though? What does this mean? I want to say that there exists a measurable family of the frame. So I want to identify the tangent space and the R to the D. But at each point, I can do that, but I want to do it measurably. So I have a measurable family of trivialization. And then now I want to say that I want to assume that G action on M is, let's say, the action alpha is the homomorphism from, let's say, diffeomorphism to M, so that I can think about the derivative. Then now I want to consider the cocycle, d alpha. Let's do not use the, okay. This is, let's say rho. The rho is the cocycle from G times M to G L dr. And how can it be defined? I want to define the rho of Gx is what? So I want to define it as phi x inverse composed with the rho of G and take a derivative at x. And then now I want to go back to Gx, the tangent space at Gx. So G dot x or G rho G of x composite with, right? Because this will map R to the D. So R to the D to tangent space at x. And then the derivative will give you the map between tangent space at x to G dot x M, and then going back to R to the D again, right? So this is the measurable map, of course, because my family of the trivialization is measurable. So this is a measurable map, and this is easy exercise for you. Actually, the rho is cocycle. So it satisfies the star. That's the thing you should check, but that's basically the chain rule. I think you can check directly.
Is it enough for me to be G quasi-invariant?
Yeah, or yes, quasi-invariant is fine, yes. Or even actually derivative cocycle, I even don't need something like invariancy, but yeah, I just assume the invariance on the definition, so that's the only reason I put the invariancy or quasi-invariancy. Yeah. Other questions? Okay, so this is one nice example, and actually this is the main example for the cocycle, and also that's the reason why the cocycle appears over and over again when you think about the group action. And again, you may have a question because your cocycle depends on the choice of your measurable family, right? If you choose different measurable family, then you will get the different cocycle. But basically, derivative is derivative. So I don't want to have two different derivatives for the same map. So that's the reason we need somehow some equivalence relation between the cocycle. So let's see. So I want to define somehow the equivalence relation between two cocycles. So here is again another definition. Alpha and beta are two cocycles. Let's say this is cocycles, measurable cocycles. We call, let's say alpha and beta. Alpha is cohomologous to beta measurably. Okay, again, for me or for this mini course, everything is in the measurable category. So I will not care about the topology or geometry right now. I'm only care about the measurable structure. So alpha is measurably cohomologous to beta if there exists measurable map such that alpha of G comma S is same as, again this is dot, inverse with beta of, this is product, this is not composition, this is product because now it is in the group, I can product G comma S and phi of S for all G and S. Again, or almost every S. So this is somehow the equivalence relation. Of course, if alpha is cohomologous to beta, beta is cohomologous to alpha. So I wrote down, in this case, I wrote down alpha is cohomologous to beta or equivalent to beta. I will denote right like this. So here the example, in this example, another exercise is that if you choose different measurable family of the trivialization, measurable family of the frame, which makes the tangent bundle become trivial, then you will get actually different cocycle. Of course, you will get a different cocycle, but it is cohomologous to the original one. You can check it very easily. So that's another exercise for you. Questions? If not, there is another important example, which is I want to call it return cocycle. And this will be related to the suspension space that Aaron mentioned. So let's say GHL, L is now closed subgroup of G. And here again, please believe me, you have a natural projection to the space of cosets. This one is fine, right? You can just map projection. You can just project G to G mod L. That's fine. The fact I want to use is actually there exists measurable section. Side. So what does this mean actually? Here, let me just write down gamma because this is the usual thing we will use. So gamma is a closed subgroup, and actually you can find the measurable section. That means actually there exists measurable fundamental domain of gamma for gamma in G. So picking a measurable section psi is actually same as the pick one measurable fundamental domain of for gamma in G. So what does this mean? You have G here, and I have a gamma, fundamental domain, let's say fundamental domain X. I have a fundamental domain, and if I choose the right translation, then I have by gamma, I have the disjoint set, disjoint measurable set, and maybe I can just translate by gamma prime, and I have another disjoint measurable set, and then now I can make a partition of G, something like this, right? For instance, if you think about R2 inside in G2 inside in R2, then I can just think about the like this. This is if you translate by the Z2, then actually this is the measurable fundamental domain, right? So there exists a measurable fundamental domain, so that G can be union of somehow the X gamma, where gamma is in gamma, and they are all measurable. So this is the fundamental domain for Z2 in R2. And now I want to define a cocycle. I want to call it the return cocycle, which is the following. The measurable map from G times G mod gamma to gamma, or secretly, actually, I want to think about written cocycle as like this. But because X is fundamental domain, so I can just identify X, and so here I want to think about X is just the image of the fundamental domain. So I want to think about X, I want to identify X and G mod gamma. So secretly, I'm thinking about the cocycle G times X to gamma, but after identification with X and G mod gamma, I can think about the cocycle G times G mod gamma to gamma. And what is this? This one will be defined by like this, if and only if Gx gamma inverse is again go back to fundamental domain. So what does this mean? So if you start with X in here, can you see? If it is too small, please let me know. You have a point in large X, but now I want to left multiply G. Then you will get somewhere in here. This is just left multiplication. Of course, you may leave your fundamental domain, but there is a unique element in gamma so that you can come back to the fundamental domain by right multiplication. So this one is not, this one is somehow something like the exercise for you. You can check that there is a unique gamma so that Gx gamma inverse can be in the original fundamental domain. That's the reason I call it the return cocycle. Make sense? So this is exercise, of course. You can check that there is a unique gamma. You can come back to the fundamental domain. And of course, this cocycle depends on the choice of the fundamental domain, right? If you choose the different fundamental domain, then maybe you will get the different map. But again, after you identify X to G mod gamma, or your fundamental domain to G mod gamma, they are cohomologous. So that's another exercise for you. If you choose different fundamental domain, then you will get cohomologous cocycle. Question?
Perhaps you want like
Where?
like G side inverse.
Yeah, but I always, I will not distinguish, yes. Yeah, I just identify G mod gamma in X, so I will not bother you with the writing side. So, yeah. But you're right, yes. I need some identification between G mod gamma and the fundamental domain.
What measures are taken on X?
Sorry?
What measure are taken on X?
Here, that's a good question. Here, let's just forget about the measure right now, because it is not really important right now. But for close-up, if you are thinking about the Lie group, let's say simple Lie group, then for a close-up group, you can find a quasi-invariant, G quasi-invariant measure on G mod gamma. Maybe it's not finite, but still. There is a quasi-invariant, maybe infinite measure, but yes, for this one, let's just ignore the measure. But at the end, we will use this cocycle for the lattice, and in there, the measure is quite straightforward, which is hard measure. Other questions? Yes? Sorry? That's actually next example. And go to the suspension. So please wait. Yes?
Concerning this question about the measure on
Yeah.
X, why you don't just take a right invariant measure on it? Why the right invariant and then you can go, it will be induced from there.
That's actually, you can do. That's one thing you can do, yes. But here, right now, I don't care about the measure too much. I don't want to think about the measure right now. But there is a definite way to do that. Yeah, of course. Other questions? Actually, if you don't have, there's one more example, but I will not do this in the board, which is the Radon-Nikodym derivative. And if there is an exercise, then I will put this on the exercise, because if you have a quasi-invariant action, a quasi-invariant measure, then actually the Radon-Nikodym derivative is also one example of the cocycle. Or if you are familiar with the hyperbolic dynamics or smooth dynamics, then there are lots of examples. There are lots of examples of the for the cocycle from the dynamics. But these two cocycles are the main example for us. Okay? So now let me give you one proposition, because this example is quite nice, right? In the sense that the cocycle does not depend on the point in S. So here's one proposition, and I will leave some of them into exercise, but here is the one proposition. So if you have a cocycle to H, so now again L is the closed subgroup. And yeah, let's ignore the measure, and let's just assume that this is, so let's just ignore the measure, and this alpha satisfies the cocycle equation star every point. So you don't need to think about the measure at all. So let's just ignore the measure on G mod L. And this is the measurable map, satisfies the star for every G1, G2, and S in the coset space. So this is the cocycle. Then actually, from here, because, and G, I need to define what is a G action. G action is just left translation. G can act on the coset space by left translation, left multiplication, right? This is the space of left coset or right coset, one of them, but you can just act by the translation, by multiplication on left. So G act on G mod L. And then actually you can define the homomorphism. I want to call it rho alpha, which is from L to H. This is homomorphism. So I want to, what do I want to do? I want to explore the relation between the homomorphism and the cocycle. So this proposition says that if you have a cocycle over G action on G mod L, actually this one is somehow transitive action. If you have a cocycle over transitive action, then actually you can define the cocycle, homomorphism, which is given by rho alpha L is defined by alpha L with identity coset. So let's say, yeah. So I will use the bracket for the coset. So this is the identity coset. E is the identity. So if you define like this, then actually you can see that this is homomorphism. You can check it. From the cocycle equation, you can derive that rho alpha is indeed homomorphism. And actually, the other direction is also true. Okay, yeah, this is exercise. So proving that rho alpha is homomorphism is your exercise. And actually, conversely, for every row, if you have a group homomorphism from L to H, then you can actually make a cocycle alpha rho, I want to say, from G times G mod L to H, which is the cocycle like this. So this one, so why do I want to present this proposition? Because basically, I want to say that if you have a cocycle over transitive action, then you can classify every cocycle. So what does this mean? So if you have a cocycle over the transitive action, then actually your cocycle comes from the homomorphism. If you have a cocycle, then you will get homomorphism. And if you have a homomorphism, then you will get the cocycle. I will give the proof of this very soon. But what's the offshot? The offshot is actually the following. Cocycles G times G mod L to H up to cohomologous is there is a bijective correspondence between cocycles like this and the homomorphism from L to H mod conjugacy. So there is a one-to-one correspondence. So sometimes we can really solve the cocycle problem. So what is the cocycle problem? The cocycle problem for me is that if you have this kind of cocycle, then can you classify all cocycle up to cohomologous? In some sense, if you have a cocycle over the transitive action, then sometimes we can do, right? And actually, the Zimmer's cocycle super-rigidity, I will tell you tomorrow, I guess. Zimmer's cocycle super-rigidity tell you that in the higher rank lattice, whatever it means, in the higher rank lattice, if you have a higher rank lattice action on some space, then measurably you can solve the cocycle. So anyway, so at least in some cases, we can really solve the cocycle problem. Questions on the statement? Okay. So then let me give you the proof of this. And of course, from here to there, you need a little bit more work, but that's your exercise. And I will not do the general case. I will only prove for the when rho is identity from L to L. I want to construct alpha identity from G times G mod L to L. So I will construct alpha corresponds to the identity homomorphism, but in general case, you can do it by yourself. That's again your exercise. Yeah, maybe I can make some PDF file for the exercise, but anyway, I will do this. But in general, almost same, or basically coming from this. So let me see. Again, I want to think about the psi. This is again the measurable section. And I will write down the cocycle, and justification is again the exercise. So if you choose the measurable section, then now alpha of alpha identity for G, comma X, you can define it as psi G dot X inverse and G psi of X. So let's see. Now this one you should, okay, let me see. This is well defined. Yes, this is well defined because they live in G, right? They are element in G. Psi is the map from G mod L to G, and X is inside in G mod L, and G is inside in G. So you can multiply the elements in G. So this is in G, this is in G, this is in G. So you can multiply, right? This is fine. But now the non-trivial thing is that why this lands into L. And that's your exercise. I think you can check. Quite straightforward. So please check. This part is the only part you should check, right? You can define like this, but then now why this cocycle lands into H. But using the fact that this is a measurable section, that means what? That means if you psi of X, and then let's say P is the projection, and this map is psi. So if you go to psi and the projection again, then you will get same X, right? This is the meaning of the section. And again, there is always, you can always find the measurable section of the projection. So you can define it, and then actually this is. And maybe there's one thing I need. I need measurable section with, maybe I need this one for safety. So identity coset maps to identity. This is not a big assumption, so you can really choose the measurable section that maps identity coset to identity. Then you can define like this, and then you will get the cocycle. Make sense?
Sorry, what did you just
So I just proved that, not prove or construct, for the identity homomorphism, I can construct a cocycle from G times G mod L to L, right? So in general, actually, if you have a like this way, if you have a homomorphism from L to H, then you can construct a cocycle over G action on G mod L, like this. And actually, if you work a little bit more, then you can classify cocycles over the transitive action. So what did I do? So let me say it this way. So what did I do? If you have a cocycle, then I can make the homomorphism. That's the direction from above to bottom, right? If you have a cocycle, then I can make a homomorphism. And if you have a homomorphism, then you can find a cocycle. This is the direction from bottom to above, right? Top. And this is the example of the construction for the identity homomorphism, but you can do it general for every arbitrary homomorphism. And for one-to-one correspondence, I already give you what is the correspondence. You should work a little bit more about the cohomologous and the conjugacy, but you can do that.
There is no relation between the homomorphism and the cocycle.
So yes, that's somehow, but this is quite special for the cocycle over the transitive action. This is not arbitrary cocycle. This is the cocycle for the G action on G mod L. So this is somehow a very special case.
I mean here, like the inverse of this implication.
Inverse of this implication is that
Yeah, you just gave the proof of this special case. There is no relation between alpha rho and rho.
Alpha rho and rho. So if you have a rho, then you can define alpha rho from the rho. You should use the rho.
Yeah. So
But that's your exercise. Yeah, that's your exercise. But I only do the identity.
I mean, you can take like something trivial. There is no additional information.
Thank you. Yes, you're right. So that rho, alpha rho is basically the rho. Yeah, so I want to say, okay, yeah, you're right. Thank you. This one, yeah, this cocycle is the what is it? Inverse direction. So yes, thank you. So cocycle, so that rho, alpha rho is conjugate to rho. Yes, sorry. You're correct. Yes. So yeah, this is really the opposite direction. Other questions? So this is one of the examples that you can solve the cocycle problem for the transitive action. Okay, so this is one interesting fact. But now, let me introduce one more terminology in order to state the Zimmer's cocycle super-rigidity later. So here's the real question. So if you have SL, say SL3Z, because we will go back to lattice tomorrow and the simple Lie groups. But let's say SL3Z. Let's think about SL3Z and what is the right envelope of the SL3Z, because that's the one question. Because if you think about SL3Z inside in something like SL100 of Z, this is not the right idea, right? This is not a good idea. If you think about SL3Z inside in SL100R, and if you work SL100R, then it's too big, right? It's somehow too big for SL3Z, right? So this is the reason why, if you think about homomorphism from, let's say gamma is a group, to GL and R, then actually if you have a representation or homomorphism, then somehow the right envelope or right group we want to consider is pi of gamma with Zariski closure. This is Zariski closure of phi of gamma. So what does this mean? Actually, you can think about the polynomials on R to the n or something like that. And you can think about the zero locus of the polynomials, right? You can think about the GLNR as inside in n times n, R, and you can identify it as R to the n square. And in here, you can define polynomial, right? Polynomial with n square variables. You can define the polynomial. And actually, you can think about the zero locus of the polynomial, and we can define it as a closed set. And that's the Zariski topology, right? So we can put the Zariski topology on here. So, and for safety, let's say SLNR, then this is a closed set, right? Because this is the zero locus of determinant of 0. And determinant is definitely the what? Polynomial, right? So, oh, 1. Thank you. Yes. So we will come here a little bit later, but if you have a homomorphism from the SL3Z to SLNR or something like that, then actually the right envelope we want to consider is the Zariski closure. We do not want to consider SL100R as an envelope for SL3Z. This is too large. So as I said that the cocycle is somehow the general version of the homomorphism, I want to define the similar notion of the Zariski closure of the cocycle. So now I want to define one terminology which is quite technical, but let me define. So I want to do similar things for the cocycle, but that means that if you have a cocycle from G times S to H, then question is that the minimal subgroup, let's say this is cocycle, minimal subgroup, let's say L. So the question is that is there a minimal subgroup L such that alpha is cohomologous to some beta, and it lands into L. So what does this mean? Yes?
I have a next question. Why is Zariski closure and not just closure, for instance?
So that's a good question. But okay, so if you take the closure, then okay, I don't have a good reason right now, but maybe I will give you the answer later. That's also one thing, yes. But yeah, let's pretend that Zariski closure is better. Yeah, I really don't have a good answer right now, but I will let you know later if I think better answer. Yeah, but it looks like here's the one naive answer. So if you think about the R inside in R2, R inside in two toroid. You have an irrational flow on T2, which is the Lie group R. The closure is T2, but this is not the right thing we want to consider. This is somehow very weirdly embedded into T2, so I don't want to consider like this. But if you consider the Zariski closure, then this kind of pathology does not appear. So that's one naive answer. What are other questions? Sorry? Here for, yes, pi to be algebraic, but yes. Yes, but yes. This is, this one should be algebraic, but yes. But yeah, this is not the rigorous one. This one will be the rigorous definition. But this is not, and also we need somehow algebraic group or Zariski topology is somehow nice because you have a Noetherian property. So in general, actually, the answer is no. You cannot really find the minimal subgroup so that your cocycle is cohomologous to other cocycle. So what does this mean? This means that there is no other cocycle cohomologous to alpha that maps into proper subgroup of L, right? In general, the answer is no. You can really shrink your target group by conjugacy. But in algebraic group category, this is true. Oh. Yes.
What's the meaning of finding L zero to be zero, the trivial solid? What's the meaning of that? If I find beta,
Uh-huh.
L equals zero because I did the trivial group. What's the meaning?
Then your L is trivial. So there's no meaning yet. Yeah, but I want to mimic somehow the Zariski closure in the cocycle level, in the cocycle language. So I want to somehow find the minimal subgroup that your cocycle lands into there, optical homologous.
My question is, what if this minimal is the trivial subgroup? If you find what's the meaning? You have a special meaning of this group?
No, I don't think that there is no meaning right now, only for that information. Okay? I just want to mimic I just want to introduce the terminology about Zariski closure of the cocycle. So for now, there's no meaning, but you will see later that is quite helpful. So in general, the answer is no, but at least in the algebraic category, you can do that. So here's the proposition. So let me see. Let's say G times S to H is the cocycle. And now I assume that H is inside in SL-MR for some R, for some M, and closed subgroup. And now I want to say the Zariski closed. So H is given by the zero locus of the polynomial. So then there exists L inside in H, which is again the Zariski closed subgroup. Such that alpha is cohomologous to a cocycle beta taking values in L. So this is the first statement. And also, this is somehow really the minimal. L is the minimal subgroup you can have as a target. So N, but is not homologous to a cocycle taking values in any proper subgroup of proper, let's say, Zariski closed subgroup of L of L. Yes, that's the end of the sentence. So what does this mean? So if your target is algebraic, I want to say that Zariski closed subgroup of SLMR, I always refer it as an algebraic group. So your H, if your target group is algebraic group, then actually you can find algebraic subgroup so that you can find a cocycle cohomologous to the original one that takes values in L, but is not cohomologous to, but alpha is not cohomologous to a cocycle taking values in any proper Zariski closed subgroup of L. Yes?
Is it true that L is going to be contained in the Zariski closure of the image of n cocycle?
No. We don't know. Yeah, we don't know. Yeah. So a priori alpha can be somehow, the image of alpha can be Zariski dense, a priori. But up to conjugation, so this is up to cohomologous. So that's the difficulty.
Yeah. But I mean, is it true that if you take another cocycle beta prime homologous to alpha,
yeah,
you look at the Zariski closure of the image,
yes,
it must contain a...
no. Again, no. So yes, this L is unique up to conjugacy. Unique up to conjugacy, and that's another proposition. Up to conjugacy. So here, L is actually unique, and L is unique up to conjugacy in H. And this is called algebraical. Or conjugate class of L is called algebraical. Algebraic whole of alpha. Yes?
Alpha is not supposed also to any, because I call it usually is in any conjugacy class, conjugate of alpha.
So, can you say again?
It's not only not come always to any cosine with value in a progressive group of L, also of any conjugate.
Exactly. Yes, yes, yes. Questions? Or yeah, I think I want to change my plan a little bit. So at first, I hope I can give the proof of this fact. It's not quite hard. Actually, the existence of L is quite straightforward because Zariski topology has the Noetherian property, right? If you have a descending chain, then you should stable at some point. And this is somehow the minimality of the group. So you cannot really go to or you cannot go forever. You should stable at some point. So existence of L is quite straightforward because of the Zariski topology. And that's another reason why the Zariski topology is better than just closure. But now uniqueness, you need to work a little bit. And this is quite hard in some sense, tricky. But yeah, if I can make it to the exercise, then maybe I will make it into the exercise. So, but I feel that I did not state any interesting statement other than that today. So maybe I write down the super-rigidity statement, and then let's start from there tomorrow. So, oops. So let me write down the Zimmer's cocycle super-rigidity first. And then from there, we will see more general version of the cocycle super-rigidity later. So the theorem by Zimmer is the following. For avoiding, again, technical difficulties, let's just think about the G is SL and R with n is only 3. So here, you need n is only 3 because of the sort of the higher rank. So this is actually for the higher rank assumption. And what does this mean? It really means that your diagonal subgroup, A, in the Margulis talk, A is not R. A is actually R2, which is diagonal subgroup. T3. And this is what is it? If you think about the maximal subgroup in G that is simultaneously diagonalizable over R, this is the maximal one, right? You cannot find R3 in SL3R that simultaneously diagonalizable over R. So R2 is the maximum, and R2 is not R, so this is 2. So that's the reason why this is called higher rank. This is higher rank free abelian group. And that's the reason I need n is only 3, because I want to get R2. Anyway, so this is the one reason. And actually, why this theorem holds for higher rank? Because you can really use the trick that Aaron used in the measure rigidity. You can really use the corner, and there are a lot. For one element, something like 1, 2, 2, 1 over 4 in SL3R, you can have lots of centralizer. So you can. That's the reason why we need higher rank for this theorem. But I will emphasize that too much. I just write down the statement. So let's say alpha, so let's say S. Now I really want to say that this is G space, so G acting on here, and mu is G invariant and ergodic. So if you have a G invariant ergodic probability measure, and now if we have a cocycle to SL-MR, M can be arbitrary. And if you assume that, let's say this is H, assume that H is algebraical. H is the algebraical of alpha. So now this is somehow minimal cocycle you can get up to conjugacy, right? I will write down the Margulis super-rigidity also. Then you can see the correspondence. Then actually we can classify every cocycle as in here. Here this is really surprising theorem because I do not assume anything on the action or space of the action. This need not be the transitive action, but still we can classify the cocycle. Let's say alpha is cohomologous to alpha pi, where alpha phi, let's say, yeah. So let me write down this way. G comma x is same as phi of G dot x inverse and pi of G phi of x for some almost every x or every x in S and G in G for some homomorphism from G to H and measurable, and this is homomorphism measurable map from S to H. So what does this mean? You can really classify the cocycle of you can really see that up to cohomology you can find a representation, so alpha is cohomologous to the representation. This will be quite useful later. And let me write down the Margulis super-rigidity. Yes? H be what? Actually, your H can be any algebraic simple group. Yeah.
Maybe you could just put the algebraic color of homomorphism is the Zariski
It is Zariski dense in here. The pi of G is Zariski dense in H, but basically that means that it is Zariski. Yeah.
I'm just saying in general. I'm asking.
Yeah.
The algebraic color of homomorphism is just the Zariski closure of the image.
Exactly. Yeah. And here is the theorem by Margulis. Sorry? H does. Yeah, I assume that H is the algebraical. The target alpha is already minimal, so somehow alpha is always Zariski dense. So I will state more about this. I will start from here later, but let me just write down the statement so that you can see some correspondence. So let's say gamma is in G. Again, G is SLNR with N is only 3. And here this is lattice. I will let you know what is lattice tomorrow, but if you are not familiar, then you can just assume that gamma is SL and Z. That's totally fine. And if you have a homomorphism, SLMH, SLMR, of course, it looks quite hard to have this kind of object, but if, yeah, this is not possible, but let me pretend that this is possible. So let's say this is Zariski closure is entire H. Again, yeah, this is not possible for large M, but let's just pretend that this is possible. In general, H can be any simple algebraic group. So, but if your Zariski dense if you have a homomorphism to algebraic group, which is image is Zariski dense, then there exists homomorphism G to H such that, which is algebraic, rho of gamma is pi of gamma. So what does this mean? You have a lattice in G. Now you have a homomorphism to H. Actually, you can lift the homomorphism. This is quite non-trivial. And actually, tomorrow is quite a little bit weird, but we will see how can we prove Margulis' super-rigidity from the Zimmer. I know that that's quite weird order, but at least that's a good idea to see how suspension works. But anyway, so sorry? H is non-compact, and I want to assume that it is Zariski. Yeah, it is Zariski dense in the non-compact group, so it is not bounded. It cannot be bounded. So if you don't have question, I want to stop here.
You discussed how to get a homomorphism from co-cycle in the homogeneous case. Let's say you take the example where you have the derivative co-cycle. What representation of gamma do you get?
So that's a good question. And actually, you cannot really use the co-cycle super-rigidity for general derivative co-cycle, because now I have a little bit weird assumption, which is algebraic whole is simple. So we will see later how you can generalize this super-rigidity to general target. So you will, please wait until tomorrow. I will show you later. But that's usually you cannot control at all. But I also have I forgot to write down one thing here. So I think this is much more related to your question. So here's one example for you. So I think O n x on S n minus 1, right? By isometry. But this is a homogeneous space. O n mod O n minus 1, right? This is the group action. And then now you can take a derivative co-cycle. GL n minus 1R, right? This is the transitive action, right? Then now based on the correspondence, you should be able to find rho of D, right? From the O n minus 1 to GL n minus 1, right? This is homomorphism. Can you find what is this? Is it just injective? Yeah, it should be trivial, but it's not trivial. It should be the injective. What is it? Injective map. So what is it? Defining representation, or? So yeah, yeah, I think this is quite fun exercise for you. What is the homomorphism you will get for the derivative co-cycle on here?
Other questions?
Just a basic question. What is the motivation for co-cycles? I mean, why do we care about co-cycles?
Why do you care about? That's good. You will see more applications tomorrow and Wednesday. But co-cycle is somehow, for me, the co-cycle is somehow the object encode dynamical information, information from the dynamics. For instance, especially for the derivative co-cycle. So derivative co-cycle, so co-cycle is somehow natural from for me, the cocycle really is natural from the chain rule. And derivative cocycle really encode some, first order information of the dynamics, right? It encodes some information about the derivative. So it is natural to think about the cocycle itself. And we will see later how this kind of solving the cocycle problem is why useful later in Tuesday or Wednesday. So yeah, it's quite weird if you see first, then why do we care about this kind of object? But yeah, you can see some of the answer tomorrow and Wednesday, hopefully.
If there's no other questions, let's thank Homin now.
Thank you.